I ask you to review these integration by parts and be able to come up with this formula. And I use the b there. And if you understand that a and b can be anything, right, as long as it's inside the domain of the function. So I'm going to treat that b as a number called x, then representing that we fix a and change that x, right? So how does this first of look like? That if at a, and first of the Taylor series or integration by part gives you f of a. The next one was first derivative at a and 1 factorial and x minus a to the first power, right? And second one was second derivative, not function, but evaluated the center divided by 2 factorial. It's coming from differentiating x minus 2 a couple times. There, this 2 factorial there. Goes on like this, right? Doesn't go on forever. You have to stop it. There's some point. This is fn and n factorial down there, and x minus a raised to nth power. So there is this lingering part in the integration by parts, right? We just integrated this part, I think, x minus a part. So that function is there, and set aside this n factorial because it's constant. Now in integration by part, you differentiate this one. So that one goes into there as a derivative. This time not at a, it's actually as a function, right? Here, because it's definite integral, you plug in x and a in there, but this remains the function inside. And there's a t minus a raised to nth power dt. So that's, if you do the integration by part n times, you arrive at here. And then we wrote this one with the sigma notation. Go to n, kth derivative at a, divided by k factorial and x minus a, nth power. So that's a polynomial part, right? This is not infinite series, a polynomial part, and there is this remainder. That's the name for this part, remainder. It's nth derivative, t minus a to the n dt. So that was homework. Okay? So if you look at it like this, and this is a polynomial, a is something that we fix, just like the power series, you kind of want to investigate around that point a, and k is this index. So if you look at this part right here, these are just a constant part relative to x, where x is a main variable function. And it stops it there, so it's a polynomial. And that polynomial has name, is Tnx, is a Taylor polynomial, not degree n, but order n, that's the name. It seems like the highest degree is x minus a, but this can be 0. Maybe the nth derivative of a is 0, then there's no nth term. Then polynomial of degree n is not the correct term, so they use the term order n. So it's nth polynomial, nth order Taylor polynomial, that's the name of it. And it stops there. There's no, if you truncate it there, that's a polynomial part. There, that's the name for it. And period. So our hope is that this polynomial part, after we went through probably 500 terms, then this thing is really major part of that one, and this one is very, very small. If that happens, and this one is the main term, in this main term, except that a part, if a and computing kth derivative are easy, if you look at it here, all we do in it here and adding and subtracting and multiplying and division. There's no transcendental calculation. So this replaces this potentially difficult function down to a basic for arithmetic, if this kth derivative a is simple enough. So that's what we have accomplished here. If this one is negligible and so on. But we don't know yet. So that's first, the polynomial part is called Taylor polynomial. And what we want to do is that we want to push that n to infinity, right? So we enter this thing, which is exactly the form of a power series. If you have this all the k's defined, why don't we push that to infinity? Then we enter this one right here. It's not n. I was wrong about this exponent n. There has to be k. It's varying the k. Sorry about that. And inside the integral, there's n in there. All right, so if you push to that, and this is an infinite series, That infinite series is called Taylor series. So I'm going to name it like this, f tilde. Suggesting that this is not necessarily equal to f of x. You can push this portion here infinity, but what about this guy? We can't just ignore that part. If we can guarantee this integral part called the remainder part, if this guy approaches 0, then this f tilde and f of x will be equal to each other. And that's what we want. But it's under the condition that this term becomes negligent as n approaches infinity. That sometimes doesn't happen. That function for which this one doesn't go to infinity is not really crazy. It's just right around the corner. We can grab it. It's just right elementary function, and this guy doesn't go to infinity. It's not hard to write it down. But some of the basic elementary functions, and they usually go to 0. So this will be eventually equal, but never think that it's going to be that, life is going to be that easy. It's actually not the same. That's why I'm introducing a new notation. Okay? And you recognize this is a power series, right? There's some coefficient that doesn't involve x in there. And here's the monomial centered at a. Okay. Now, what I said is this remark, is important remark about this, our goal. Our goal is that this function value f of x, like sine x and cosine x, and something difficult to compute, is that ever going to be this power series. And then you can quickly write this computer software program and calculate. This is a basic arithmetic, and get a very precise value of sine and cosine and tangent and e to the x, so that they have this table of precise values of just ready for construction of an electronic calculator, things like that, right? You don't have to measure anything. It's just that. So what is the condition? Is that first this guy should make sense. So the radius of convergence for infinite series called f tilde is good. Namely, should be positive, right? Radius of convergence is 0, then it's just a, it's nothing. You've got to have some nice positive so that we can have some x can plug in and become a meaningful number. What is the second condition? Anybody remember? So for these two things being the same, what is the second condition? That remainder term got to go 0, so that this one is going to approach an infinity, becomes exactly the same to the left-hand side. So this remainder part with n factorial outside, a to x, and this much of the derivative integrated along with this product approaches 0. Okay? As what approaches what? This approaches 0 as what approaches what? N, as you add more and more term, right? So is n approaches infinity. While when you're doing this business, sending this one to 0 while x is fixed. That's the important part, right? X is not changing. X is some value. We're going to estimate, and then you add more and more term, and if this guy's approaching 0, boom, we're in a good situation. F of x is going to be eventually equal to f tilde. F tilde is going to be eventually equal to f of x. Make sense? All right, so let's look at example to get this one. So to see this one go to the 0, I'm going to introduce a little bit of result. I think it's a really efficient way of doing this. So here's something familiar thing, is a ratio test. All right. So ratio test for sequences. Okay? The ratio test, you remember, is a ratio test for series. Some of this thing are doing the ratio test, right? Here's a ratio test for the sequence. So here's what I mean by that. I have sequence AK divided by AK, right? And that approaches number L, and that is less than 1. That looks like exactly the ratio test of the series, right? And AK is the term. What is the conclusion about? Not about the series, but about this AK. Where is the AK supposed to go? If it is like this, the series converges, is that right? Series converges, right? What do we know about any result about the tail term when the series converges? This is known as the divergence test. But the flip side of the divergence test approaches 0. Had no choice. If something converges, AK must go to 0. So if you want to show something go to 0, maybe you can just take the ratios and see where it goes. If it goes to something less than 1, you conclude that that one goes to 0. All right? And especially if it has a factorial in there, ratio is a good idea, right? Factorial cancels a lot with the ratio. That's why I'm introducing this one. So let's complete this one. Do we have some result on that AK approaching L that is 1? Then what happened to the AK? Absolute value of AK it actually goes to infinity. Not only not going to 0, we have a more specific information. It actually goes to infinity. If it approaches 1, inconclusive. There are lots of examples. It's different result. This is a useful observation, readily available from our ratio test of a series. Okay, so let's look at examples. And running out of space, I'm going to copy some of these, and I'm going to continue in 2 minutes. All right, I took this example e to the x, and our goal is to look at Taylor series, and especially pay attention to the remainder, and verify that remainder is actually negligent. But before you enter this series, Taylor series, you have to think about the choice of your center. This e to the x expand to negative infinity to positive infinity. What are we going to base it on? Are we going to look at 0? Are we going to look at 1? The principle is that we have to calculate these guys when you calculate the Taylor series, right? Kth derivative at a. And we want these things to be something simple. You make this choice A such that this guy is easy to calculate. If this is more complicated than what you're trying to calculate right here, there's not much of a point of actually doing this business. If it is not exact calculation, then you can base it on anywhere. You're going to use a calculator anyway. But if you have to be hand calculation, you want to be need result, it has to be simple for your choice of A. And if you look around, maybe e to the 0 is 1, maybe that's going to work. So when a equals 0, seems like everything is simple. So you make that choice. My a is going to be 0 and see if really everything is going to be simple enough. In that Taylor series, if I'm going to show you the Taylor series again, this is a formula of the Taylor polynomial. And this we're going to push that to infinity. All that you need to figure out here is a kth derivative of a. So you have to write down the formula of the kth derivative. Function we're about to enter exhibit very clear pattern in that. So there's no formula. Write down a first few derivative and then you pick up that. And this is also a homework problem. So what's the first derivative? E to the x, right? Second derivative? E to the x. Fantastic. You don't have to go to any further. It's always e to the x. That's the property of e to the x, right? Then what do? We evaluate f, I'm going to do it here, f1 over 0. That's our base point, right? And that's 1. Is that right? E to the 0 is 1. And second derivative, still e to the x. If you plug in 0, that's 1. And you can see this is a forever 1. So I can write down this kth derivative at our base point 0 is always 1. It's not changing with respect to k. So that's something very special about e to the x. Probably the simplest Taylor series ever, right? And in terms of calculating the values of a derivative. Now you go to Taylor series there. Recognizing this is not necessarily yet equal to f of x, so use different notation. Taylor series looks like this, going from k to 0 to infinity. And x minus this times is 0, so I'm going to first write it like this. And fk, kth derivative, evaluated to 0 and k factorial. This is the very formula, and we know the numerator is always 1, right? So how does that simplify? Is k going from 0 to infinity, and 1 divided by k factorial times x to the k, right? That is called a Taylor series. So is that going to be exactly f of x? It depends on this remainder, guys. I'm going to use the standard notation. They use this Rn, this remainder for arbitrary n is 1 over n factorial, is integral, right? Going from where to where? Our base point is 0 to x, correct? And here's the n plus first derivative, correct? Let me show you again. Here is the shape of the remainder part. N factorial down there, n plus 1 derivative. What is the n plus 1 derivative here? It's e to the t, right? You did that normal. Next part is a t minus 0. So it's going to be t raised to nth power n dt. All right? Actually integrating this one will be a lot of work, right? It's, you have to do recursive relation and all that. Is going to be very, very complicated. You will see that it's even more complicated what you're trying to do. All we want is this one is approaching 0 to come up with a nice upper bound that pushes this one down to 0 and use the squeeze theorem. So the question is that going to go to 0 for fixed x value? All right? So let's look at it here. Absolute value of Rn. We're not going to calculate exactly, but we're going to come up with a nice inequality that pushes down to 0. The polynomial part is easier to integrate, so you get rid of one of the factors, whatever that is. I didn't think about it that way, but it came to me. So I have two choices. I'm bounding this both, and you can kind of replace this one with a maximum value, replace that one with a maximum value. It doesn't matter which one you ever do. All right, so I'm going to do it in a standard way. They usually keep this portion and actually integrate and replace this one with a constant. Okay? So you see that is 1 over n factorial. We're about to replace this e to the t with a number. And we keep that t to the n and dt. In this integral, t varies from 0 to x if x is a positive. If x is negative, it goes to the other side, right? So it's a bit inconvenient to write all of them. So let's suppose at this point just x is a positive number. As t varies from 0 to x, and e to the t is an increasing function or decreasing function. Think about exponential function. It's exponential growth function. So starting from 0 to x, the maximum value will be obtained right at here, e to the x. So all those e to the t is never bigger than e to the x. Okay? So depending on this x, I replace this e to the t with the maximum possibility. If you replace that in integral, it gets bigger. So that's why it's not equal, but it got bigger, right? Now there's no t that you can factor that out, e to the x n factorial, then you have a 0 to the x and t to the n dt, right? And put an absolute value around it. If x is positive, and this is going to be all positive, so I keep it this way. So we know the antiderivative of this one, e to the x is there, n factorial. This one, antiderivative, turns out is the x to the n plus 1, and you plug in x equals 0, so this is what you end up at. Okay? So what is this? E to the x times x to the n plus 1. I'm going to set aside e to the x because there's no n in there. So e to the x set aside, and x to the n plus 1 up there. And what's down there? N factorial together with n plus 1. Isn't that n plus 1 factorial, right? N factorial is 1 through n. You have one more term multiplied, n plus 1. So it's n plus 1 factorial. Make sense? And we want to show this one approaches one number? 0. So that Rn, not exactly, but it pushes down to 0 by squeeze theorem. So this is where you apply the ratio test. We're going to look at this whole thing as some sort of sequence AK. Okay, and apply ratio test. So after this ratio test, don't get confused with the ratio test for the series, all right? And it's slightly different. We test the same thing, a slightly different conclusion. So AK plus 1 absolute value divided by AK. So this whole thing with k plus 1. So you see that e to the x is common. How about x to the absolute value? K plus 2. Is that right? K plus 2? I'm going to do k plus 2, sorry. And down there is n k plus 2 factorial. I replace all the k's n's with a k plus 1. And reciprocal of this exact thing with the e to the Okay, it's e to the x, what is it? X to the k plus 1 and k plus 1 factorial, right? So e to the x cancel, what do you get? K plus 2 factorial survives, right? Down there. All the way up to k plus 1 factorial, they're all common and cancel. How about this x to the absolute value there? This one, k plus 2 copies and k plus absolute value of x, 1 copy survives, right? So x is fixed and only k's are changing, and what happened to that guy? It's approaching 0. The ratio is approaching 0, not ak, right? This is the L value, and it is less than what? Less than 1. That was the ratio test right there. If it converges to something that is less than 1, and you conclude that sequence is approaching 0, because the series is approaching 0, approaching some convergence. So you recognize that it's not what approaching 0 is, approaching number that is less than 1. That's the point of it. From that ratio test, says AK approaches 0, right? But what was AK is this one in here. Okay, so we show that, therefore, this 3 dots is an international symbol for therefore, as Rn, absolute value is less than e to the x times x to the n plus 1 divided by n plus 1 factorial, and we just show that using the ratio test, this guy approaches 0 as n approaches infinity. Therefore, Rn approaches 0. And we show that the tail part is actually negligent. Therefore, Taylor series f of x, which is e to the x, right? And f tilde x, that's the Taylor series, which looks like this, k going from 0 to infinity of 1 over k factorial times x to the k. And remainder is not important anymore because we show that it's 0. So we have this thing. And there was no condition on x when you concluded that. And you can separately calculate radius of convergence. Turns out it's infinity. Okay? How do you calculate radius of convergence? You calculate that ak plus 1 with this simple 1 over k factorial, right? And then it turns out it approaches 0. No matter what x is. So all the x converges. So that's that function. And application.